minus 3 is minus 2, which means that I is just equal to 2 amps. So the total current through the circuit is 2 amps. Well, through here, right, I1 is a current of 1 amp going in this direction, and current 2 is 3 amps going in this direction. Make sense? Okay. And so that is how you do Kirchhoff's rules on a more difficult circuit to analyze.
Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button.
Okay, lecture 109, Kirchhoff's rules for DC circuits. So last lecture we learned how to combine resistors, whether they're in series or in parallel, into an equivalent resistor to simplify the analysis of circuits. And that will work a lot of the time. But what about something that looks like this? What about a circuit with 2 batteries? So our technique of combining these 2 resistors that are in parallel right here would not work because the potentials are different. And the potentials are different because of the insertion of this additional battery here. So today's lesson will be regarding Kirchhoff's rules, which are 2 rules that provide a technique to solve problems like this in a rather straightforward and systematic fashion. Okay. So the first rule is called the loop rule, and it basically says that the sum of the potentials around a loop is equal to 0. So that basically comes from the fact that the line integral of the electric field, with the electric field being a conservative field, is 0. And again, we go back to that example where if we imagine putting 2 charges in space, right, let's say they're both positive, right, and we started some configuration like here, and then we do some work to move this charge closer to this one, right, that would require actual work because they're repelling each other. But then I get that work back if I allow the charge to move back to its original position. And so that's basically the origin of this. The second of Kirchhoff's rules has to do with current through a junction. So how are we going to write this? We'll write that the current I into a junction is going to be equal to, we'll say the sum, and I'll write a little I, of the currents in each of the arms, not junctions. It's the sum over the arms. So write it like this. So what does that mean? Well, that means if I've got, say, a wire, and then it breaks off into 2 separate paths, call this the current through arm 1, and this the current through arm 2. Kirchhoff's second rule just says that the total current I flowing into this junction, which I've identified with this point, is equal to the sum of the currents in the arm. And that makes a lot of sense. If you think of, instead of wires, think of a pipe, right? And then you've got one big pipe, it's got water flowing through it, right? At some current, right? That means that a certain amount of water is going past a point per unit time, right? And we put one of those, those splitters, those pipe splitters that turn one pipe into 2 pipes, and you got 2 pieces of pipe coming out of the one pipe. There's a name for this, I just can't think of what it is. The current coming out of each of the 2 pipes at the end, if you add that up, it'll be equal to the current in the big pipe before the junction. Does that make sense? So let's do it this way. So we do 2 experiments, right? I've got a pipe, and we've got water flowing out of it, and I put a bucket underneath here. See how much water enters the bucket in some period of time, say maybe 1 minute, okay? And I measure that, and then everything stops. So I get that measurement. Now, if I had one of these branches, right, such that I had my 2 pipes, and let's say that I found a way that they could, well, I guess one would have to be a little bit longer. So both of them could dump water into, a bucket. In the same period of time, I would find the level in the bucket would be exactly the same. Does that make sense? Yes. So that's how we'd measure like the current. We'd take a bucket, we'd see how much water goes into it in a certain period of time, say 1 minute, and that would give us a measure of, maybe it's in liters, so we'd have like liters per minute. And the number of liters that would enter into the bucket in this system with the one pipe would be exactly the same as the amount of water that enters into this bucket in the same period of time using these two arms. Does that make sense?
Yes.
Okay.
Our last homework was lecture 107. It says, was there one in the middle we didn't get homework for?
You should have a homework assignment for lecture 108. If you
Most recent assignment, I think.
want to, let me see it. Let's see. Yeah, this is the running in the rain one. Last time we talked about series and parallel resistors, so you should have a homework assignment that asks you to, solve problems along those lines. Check with me after class. Okay. So let us apply this to a simple system. Let's look at the real battery that we talked about last time. I'm going to put my little resistor here. I'm going to call this little r. And then I'll have my bigger resistor, which I'll call big R. That's the load. I'm going to set the EMF of this to be, I think, 6 volts is what I used in my calculation. 6 volts. So how do we apply Kirchhoff's laws to this? Well, the second law, since there are no junctions, right, is not going to be of much use to us, right? The current is just the current. But the second law says, okay, we're going to sum up the potential drops around the loop. It doesn't matter which direction you go, but it makes sense to go in the direction of current, which would be starting from this positive post, right, and moving through the circuit like this in a clockwise fashion, yes?
Yes.
So if we start here, at this point here, right, what happens? Well, we go across this battery, and we're going to get a jump, right, from the EMF. So, and it's positive, so I'll write it as a positive number. And then after we move through the battery, we then move through the internal resistor of the battery, little r. But that, of course, is a voltage drop. And so, because we're going in the direction of current, when current goes through a resistor, the voltage drops. So this will be minus I times little r. And then we continue on around. Remember, we are ignoring the resistance of the wires because it is negligible. And so we continue around. The potential hasn't changed until we get to this big resistor R. That's the load. And so that will be a voltage drop of minus I big R. And then finally we're back to where we started again. And so Kirchhoff's first law, or first rule, says that the sum of these parts should be equal to 0. Or another way to say that is that E is equal to I times R plus big R. And so if I wanted to know what is the current through this circuit, I could solve for I. That would tell me that I is going to be equal to the EMF over R plus big R. And now I would need to ascribe some values to this, because I said we have 6 volts EMF. So I can put my 6 volts up here. Let's let little r be 1 ohm. That would be a very big resistance for a battery. And let's let big R be equal to, let's say, 11 ohms. Because when I do that, in my denominator, I get 1 ohm plus 11 ohms is 12 ohms, right? So I have 6 volts divided by 12 ohms. And so that's going to be equal to 1/2. And since I use units of volts and ohms, I'll get an answer in amps or amperes.
Okay.
I could then ask, if I wanted to, just to take the analysis a little bit further, what is the voltage across the terminals of the battery? And so remember that the battery we're modeling as this seed of EMF combined with this internal resistance. That doesn't mean that there's an actual resistor. I think people get confused about that, and I didn't really emphasize it last time. It doesn't mean that inside the battery there's a little resistor. You could replace it with a bigger or smaller resistor. This is really due to the physical makeup of the battery. Okay, it's going to have a lot to do with the chemical kinetics inside the battery, the reaction that's taking place. But it'll also have things to do with what the electrodes are made of and stuff like that. But if I were to connect, say, a voltmeter across the terminals of this battery, I would be connecting it to this point here and this point here. Well, that's the same as this point here and this point here, right? So the voltage across the terminals of the battery is equal to the current, I, times R, this R right here, big R. So I already have a current I calculated. That's 1/2 amp. And then the resistance is 11 ohms. So that's times 11 ohms. And so we get 11/2 volts, which is less than the 6 volts that you might have thought the battery would be. The EMF on the battery is 6 volts, yes, but because of the internal resistance, right, there's a voltage drop, you see? And so you're not going to get exactly the same amount. Right. Does that make sense? That the terminal voltage will be different than the EMF, right? It's because of the internal resistance of the battery?
Yeah.
Okay. Let's think about the power dissipated in this circuit for just a minute. So remember, the power is going to be the EMF times the current. And this should be equal to I squared R, that's for the internal resistance, plus I squared big R. You see that?
Yeah.
We know what I squared is. Well, 1/2 squared is 1 over 4, right? So that'll be 1 over 4 times R is 1 ohm. So that will be 1/4 of a watt. And over here we have I squared again is just going to be 1 over 4, because 1/2 squared is 1/4, times this time 11 ohms. So this will be, I'll write it as 11/4 watts. And the total power dissipated, well, if you just simply add these two up, we get 11 quarters plus 1/4 is 12 quarters. So that would be a total consumption of 3 watts. As far as Kirchhoff's rules go, this was a pretty easy problem to apply. We just added up the voltage that drops or increases around a loop in the circuit, yes?
Yeah.
So let's do a harder one and see where some of the complications arise. So I've drawn a slightly more complicated circuit with 2 batteries. This one is an 18-volt battery. We're going to assume these are ideal batteries, so we will not complicate things with internal resistances. And over here we have a 12-volt battery. And I've labeled points around the circuit. And the reason I did that is because I want to talk about what loops can we find in here, right? Because remember, Kirchhoff's first rule is called the loop rule. And so we need to look for loops in this circuit, okay? And we can label the loops. So how many possible loops can we find? Anyone want to take a guess? I mean, I'll give you a hint. The first loop would be a big loop like this. And we could call that loop 1. And it would be A, B, C, D, E, F. A to B to C to D to E to F.
Yes.
And then back to A, of course.
Does B to C to D to E to F to A count as another loop?
B to C to what?
To D to E to F to A count as a different loop?
Well, that would, well, no, that's the same loop. Same loop. But here's the second loop. Let me show you a second loop, then you'll probably figure out what.
A to F to, what is that? E to B to C to D. No, that doesn't work.
All right, A to B to E to F. That's a loop.
Yeah.
A to B to E to F. Another loop would be, doesn't matter where you start, but we'll start at B. B to C, or let's like to use the battery as a gauge here. So go D to E to B to C. Loop 3, D to E to B to C. So it turns out those are the only 3 loops in here. Yeah, let's talk about what the current situation is. Well, pick a battery. I'm going to pick the biggest one, just makes sense. So I'm going to say this is where I'm going to start, and I'm going to look at the current flowing through here. So we'll start out with the current I. And as we move across this resistor, we come to this junction B, where we can go one of 2 ways, right? We can go straight on to C or down to E. So we see we have a place where the current splits right here. And so we can call this maybe E1, and we can call this, not E, I1 and I2. And that is pretty much it. Okay, that takes care of our currents through this. We only have the one splitting point, which is right here.
Yeah.
So we can say that Kirchhoff's second law, right, is going to tell us for sure that I is going to be equal to I1 plus I2.
Okay.
So that's an equation that we have at our disposal to solve this system. But now we need to, we could use all 3 loops, but we don't really need to. We've already got 3 equations plus this other equation here, right? So we're not going to need all 3 loops. Yeah, so let's start with loop 2, right? Loop 2. What does that tell us? Well, let's start here on this side of the battery, so we get the plus 18 volts. Then we go across this resistor here. That's going to be a drop of I, big I, just regular I, no subscript yet, times the resistance 12. So I'm just going to write it as 12I. Minus 12I. And loop 2 next goes down here, crossing this resistor of 6 ohms, but this is current I1. It's still a drop, though, because I'm going across in the same direction that current is flowing, you see?
Yeah.
If I had been going this way, I would change the sign. okay, because the current would have a different sign. But anyway, so here we're going to, again, drop by 6 ohms this time, so 6, but not I, but I1. And this equals 0. That's loop 2. Let's look at loop 3. Well, loop 3 is D, E, B, C, okay? So going from D to E, which direction is the current going here? Look at the current in this circuit, right? Here's the positive pole of the battery, here's the current flowing into it, you see that? So it's going around this way, so this will be a voltage drop. It'll be minus 1, because 1 ohm, times the current. But the current is I2, right? Minus I2. Then we get to go across this resistor, but this time we're going in the opposite direction that the current is flowing. So it'll be plus 6, because 6 ohms, times I1. And then we get to B, and we go back across this 1 ohm resistor here. Since we're going in the same direction as the current, it'll be minus again, and that's minus 1 ohm, so 1 times I2. And then finally we go across this battery, but look which way we're going across the battery. We're going, well, okay, we're going from the minus to the positive, so that will be plus 12 volts, okay? And this will equal 0. Now we could do the big loop, loop number 1, and add that to it, but that would be a bit of an overkill. We don't need that much, because what I want to do with this is set up a system of equations, because I already have 3 equations and 3 unknowns, right? Here's one equation,
Yes.
yeah? And then here are 2 more. So there are my 3 equations. So what I want to do is I want to put this into a system of equations. And remember, these, if you were to graph them, these are just lines, right? Do you remember that a system of equation is just asking where lines intersect? If I have a couple of equations for lines and I want to know when those 2 lines are simultaneously satisfied, it's equivalent to asking the question, well, if I were to graph these 2 lines, here's line number 1, and maybe here's line number 2.
Yeah.
To solve a system of equations of these 2 lines is to ask where these 2 lines cross. Do they always have to cross? No. Your solutions will either be one solution, like this. If instead of that line, the line that we had was one that was parallel to the first line. That's a terrible parallel line, but it never crosses. So there are no solutions to that one, right? And the other possibility is if the second line that you had, though you didn't realize it, was really just exactly the same as the first line. So they're equal to each other everywhere. They're like on top of each other. Yes?
Yeah.
And so in that case, every solution is a solution. So these kind of things are most easily solved using matrices. I think most people have seen matrices in linear algebra for doing a solution of linear equations.
So the general idea is, instead of writing the equations like this, we can instead put it in matrix form. We can then do a row operation, taking row 1 minus row 2. We can then divide row 2 by minus 1. And finally, add 2 times row 2 plus row 1 to get our solution, x equals 2, y equals 1, which corresponds to the point on the graph shown here.
Anyway, so what we want to do is we want to write these in kind of a matrix form. The coefficients that correspond to, so the column, this is the I column, right? So I've got 1I from Kirchhoff's second rule. Then I have 1 times I1, so 1 here, 1 times I2, so 1 here, and then 0 here. Oh, but my sign is wrong. Sorry. This minus this. So this should be a minus 1 and minus 1 here as well. Then I'll put in loop 2, so we'll have 2, because that's the coefficient in front of I, 1, because that's the coefficient in front of I1, and 0, because that's the coefficient in front of I2, and equals 3. And then the last entry, the last row, will be loop 3. So I'll have 0I, so 0 here, minus 3I1, so minus 3 here, plus I2, so just a 1 here, and that's equal to 6. So now I have a matrix that I can solve. And you might remember that, if you want to get it totally solved, you would get it, I think it's called reduced row echelon form. But you don't even need to go that far. If you could just get like triangular, right, lower triangular, then that's good enough to solve these. And so that's what we're going to try to do here. So the first thing we can do to manipulate the row, do row operations on this, right, is I'm going to do the middle row. So I'll leave the first row unchanged, 1, minus 1, minus 1, 0. But on the second row, I'm going to do 2 times the first row minus the second row. And you can see why I'd want to do that, because if I multiply the first row times 2, that's going to get rid of this first entry here, right? So 2 times the first row. Well, that's 2 times 1 is 2, minus 2 is 0, so I get 0. Then I'll do 2 times minus 1 is minus 2, minus 1 is going to give me minus 3. And then 2 times minus 1 is minus 2, minus 0 will just stay minus 2. And 2 times 0 is, 2 times 0 is 0, minus 3 becomes a minus 3. And then the last row I'll just stay the same, 0, minus 3, 1, 6. That's unchanged. So what can I do now? Because I want zeros in front of all of the diagonal terms here, right? So we can use the second row, obviously, right? So we'll leave this 1, minus 1, minus 1, 0. That will give me 0, minus 3, minus 2, minus 3. And if I just simply take the first row minus the third row, then that should give me what I'm looking for. So R2 minus R1. The second row minus the third row. So this minus this is 0. Minus 3 minus minus 3 is minus 3 plus 3, so that's 0. And then I have minus 2 minus 1 is minus 3. And minus 3 minus 6 is minus 9. And so now we have enough information that we can really solve this thing, right? We could take, for example, this equation here. The last row in here says that minus 3, that's I2, is equal to minus 9, right? Solve for I2, that says that I2 is equal to 3 amps. So I2, the current going through loop, what do we call it, BC, DE, or DE, BC, right, is equal to 3 amps. We can use the next one up in combination with the one we just got, because the next row tells us that minus 3 I1 minus 2 I2 is equal to minus 3. We already have I2, that's 3 amps, so this becomes minus 2 times 3, or minus 6, right? So minus 6. So we get minus 3 I1 minus 6 equals minus 3. So we can add 6 to both sides. Gets rid of the 6 over here. And minus 3 plus 6 is 3. And this says that I1 is equal to minus 1 amp. Now what does the minus tell us? That says that we got the direction wrong in our diagram. It's no problem. It just says that the current is flowing in the opposite direction that we thought it was. That just fell out of the analysis using Kirchhoff's rules. The fact that we have a negative sign here just means I1 is going this way and not the way we thought it was originally. Had we put in the direction correctly, it would have been different. But anyways, so it doesn't matter which way you pick for the directions, you're going to get it right because the analysis will tell you. If the sign changes, then it means your direction was wrong. Does that make sense?
Yeah.
Okay. And then finally, the last equation is just the continuity of charge equation. And that tells me that I minus 1 times I1, which is this, so minus that, it'll be plus 1, minus 1 times I2, but I2 is 3, so that's minus 3 equals 0. So 1 minus 3 is minus 2, which means that I is just equal to 2 amps. So the total current through the circuit is 2 amps. Well, through here, right, I1 is a current of 1 amp going in this direction, and current 2 is 3 amps going in this direction. Make sense?
Yes.
Okay. And so that is how you do Kirchhoff's rules on a more difficult circuit to analyze. Right? Now, did you have to use the matrix method? No, you didn't. You could have just simply plugged these equations into each other and tried to solve them directly. You could have solved this equation for, say, I1 and substituted that value into I1 in loop 2 equation, right? And then substituted, you know how to do that, right? So the substitution method for solving a system of linear equations. It's a system of linear equations, so you solve them in whatever way you're comfortable with solving them. But I just wanted to illustrate it using the matrix methods because I think that that's usually cleaner, less prone to error. But who knows? I usually make errors when doing these kind of calculations, so I'll do them at least twice just to make sure they're right. And so I suggest you do the same. Okay, any questions? Any points of confusion?
What about the loops? Why are there only 3 loops? You can imagine more loops, and what qualifies as a loop?
what qualifies as a loop? Well, that's a good question. Maybe one of the rules for deciding what is a loop is you say you can't pass over the same point more than once, right? And that you have to return to the point that you started from. So for example, this is excluded as a loop because I passed over this point B twice. So there would be redundant information that you could write it as a loop, but it would, you'd end up, when you're adding in terms, right? So let's say I did a funky loop like that, right? Whenever I went across the first time, so I went from A to B to C, let's say. So when I go from B to C, because I'm moving in the direction the current is, right? Well, actually, I don't want to stop with this one. I went from A to B, I crossed this resistor here. And because I'm going in the direction that the current is going, I'm going to subtract that voltage drop, right?
Yeah.
But when I come back around, I then go to C, and then to D, and then to E, then back up to B, and then back across here again, right? When I do that, when I cross back over, I'm going in the opposite direction that the current is, and so I'm going to add back that voltage drop. It effectively removes it. And so what I end up finding is that this loop I thought I had, which was A to B to C to D to E to B to back to A, was really the loop B to C to D to E and back to B, right?
Yeah.
You see?
Yes.
Yeah. So, but it's a good question, right? How do you, usually you kind of look at it and you're kind of intuitive about it, right? You're like, well, here's a loop, and then there's the big loop. Everyone always forgets the big loop. I think there's like a puzzle problem that people like to put on the internet that has something, a theme similar to that, where they always miss the big loop. But yeah, so usually it's going to be intuitive and you'll figure it out. Any other questions? No? Okay, well, that's it for now. Next time I was going to talk about RC circuits in this lecture, but I decided that I wanted to go into a little bit more detail on exponents, well, really on exponential growth, because sometimes that's not covered until later in, say, a calculus course, for example, and it's usually only covered minimally in algebra and pre-calculus courses. So I want to spend a little bit of time talking about exponential growth, and then we'll talk about RC circuits in that same lecture. So I wanted to leave room for that. So we'll do that next week. All right, see you then.